I realize people are pretty tired at this point in the conference, and so to keep this talk lightweight, we're going to play some games. And the reason for this is because we believe that by playing games, we can solve the device drivers problem, which is that drivers are difficult to write, they are difficult to debug, they tend to have a lot of bugs, and they're a major problem for both OS vendors and hardware vendors. And one evidence of this is the fact that this project is proudly funded by a research grant from Intel. So our approach to the problem is based on a very simple observation. Namely that as a driver developer, what you do is largely dictated by two specifications. The specification of the interface between the driver and the OS, and the specification of the device. And so the driver must take a request from the operating system and convert it into a sequence of commands to the device. And it turns out that in between these two specs, there isn't that much that you can do in different ways. There isn't that much flexibility in terms of how the driver can control the device. And so driver development is a tedious and error-prone, but at the same time, largely mechanical task. And as such, it's a perfect target for automation. And the way we automate it is by approaching the problem as a controller synthesis problem. The idea is you look at the driver as a controller for the device, and you look at the device as this finite state machine where some of the transitions are controllable, they can be triggered by the driver, whereas others are uncontrollable, things like error conditions or arrival of data from the network, and those are shown with red arrows here. So the driver takes a request from the OS, and in response to this request, it must force the device state machine into a particular state. And it must be able to do so regardless of the uncontrollable things that happen inside the device. And this can be seen as a game, where the driver plays against the device, and the driver plays the game by making controllable actions, whereas the device plays by performing uncontrollable actions. A winning strategy for the driver in the game guarantees that it will always be able to handle any OS request for any possible uncontrollable device behavior. So there are a few reasons why we're really excited to work on this project. So first of all, it addresses an important problem, obviously. Second, we feel that it's a simple and nice idea. I mean, I already explained it to you in a couple of sentences, and I'm hoping it made sense. The fact that we can take this messy, difficult, real-world problem and formalize it in a nice and principled way as a game, to us it's an indication that we're on the right track. This is one of very few applications of formal methods to operating systems beyond verification. And in fact, it is the first time that game-based synthesis is used in the operating systems domain, to the best of our knowledge. Finally, we are pretty thrilled by the fact that most people consider driver synthesis to be impossible. In fact, when we started this project a few years ago, we weren't sure at all exactly how we're going to take this vision to a practical tool. And of course, Andrew Tannenbaum was the one who formulated our concerns in the best possible way. He approached our poster at one of the conferences and he said, "This is a really good project, I really like it. Now this is impossible, this is impossible, and this is impossible. Otherwise it's really good." And then he walked away. And so we thought, after all, research is supposed to be about pushing the boundaries of what's possible, so we decided to keep pushing this research agenda. So let me use a very simple example to explain exactly how drivers are like games. We're going to use an example of a real-time clock device, which can be found on any computer. For illustration purposes, I'm going to visualize it as a real alarm clock. So we want to write a driver for it. And one of the things the driver has to do is it must handle an operating system request to set the time value to some user-provided new time. One way to complete this request is to first write the hours register, then minutes, then seconds, and we get exactly the time that was requested. And the driver that works this way will be working just fine most of the time, except that there is a slight possibility that somewhere in the middle of the sequence, a clock tick will happen. And it will increment the number of seconds, which in this particular case will also increment the number of minutes and hours to the next value. If we then continue our sequence and write minutes and seconds, then we end up with a time value in the end, which is 1 hour off what was requested. So this shows that correct driver must be able to handle any possible device behavior, not just one particular one. In this case, one way to write such a driver is like this. So we start with stopping the oscillator in the clock so that the time doesn't change automatically. and then we set the new time, and then we restart the clock. So this driver will work correctly in all cases. Now let's look at the same driver from the game perspective. So we start in the initial state with some kind of time value set inside the device. We get this request from the operating system. And now the goal of the driver is to force the device into the state where this new time value will be set. And the question, is there a strategy that does so? Of course, there are many other states and transitions in the system. So transitions are uncontrollable, like clock tick, shown with red arrows, or controllable, shown with green arrows. By definition, we know that this final state is correct, is a winning state. This is where we want to be. We also know that this state is losing because we end up with the wrong time value. We can prove, for example, that this state is also winning because there is a controllable transition from this state to the goal, so we can get into the goal in one step. If we then keep backtracking from the goal in the same manner, we will eventually find all the winning states in the game. And then at the very last step, we look at the initial state, and we realize that there is only one uncontrollable transition from this state, which always goes to the state we already know is winning, this one. So we can finally conclude that the initial state is winning and that there exists a winning strategy in the game. So that's the main idea. We developed a driver synthesis tool called Termite. I wrote a specification of this device and the operating system interface in the device specification language. I gave it to Termite, and after a few seconds, Termite comes back with an answer saying, first of all, there exists a winning strategy for the driver in this game. Second of all, I computed the strategy. And so now Termite is ready to start converting this winning strategy into source code. So we start with the empty template for the setTime function. So the dots there, they are a placeholder where the synthesized code will go. And then the first statement that Termite synthesizes writes a control register, which happens to have the effect of stopping the clock oscillator, so what we discussed before. It then writes hours, minutes, seconds, then it restarts the clock. And this is exactly the strategy that I presented. Now, you might notice that instead of synthesizing the whole thing in one go, we are going statement by statement. And this is actually a fundamental feature of Termite. Our first implementation of the tool, presented at SOSP 2009, was fully automatic push-button synthesis. The idea was you start with the correct specification, the code is generated automatically, it matches the spec, hence it's ideal, flawless code, and there is absolutely no reason for the user to be involved. But turns out that it never works like that. It turned out that there are many reasons why this kind of push-button approach doesn't work, but all of them boil down to the fact that it's never a good idea to take control away from the developer. Because then you end up with problems like it's hard or impossible to choose between multiple functionally equivalent options for implementation, for example, between polling versus interrupt-based request completion. It's difficult to enforce non-functional properties like power, performance, timing, and so on. It's difficult to achieve nice and user-readable code structure. And while each of these, there are a lot of things that could be done to address each of these points, altogether they sort of indicate that the whole paradigm must be reconsidered. And so we came up with a different approach to synthesis, which we call user-guided synthesis. The idea is that user is always in control. The user can write arbitrary manual code. The user can modify any of the generated code. The tool behaves as a very smart version of code autocomplete. It is so smart it can actually write the whole driver for you, or a whole function, but it will not only do so on demand, and it will do so without ever changing anything that the user wrote by hand. Instead, it will take this implementation and will try to extend it to a complete driver implementation. Importantly, it enforces correctness. So although in the end your driver consists of some kind of mix of manual and automatic code, Termite will never allow synthesis to complete unless the resulting driver satisfies the specification. So let's see how this works in practice. So we go back to our example, to the demo. And let's say that as a developer, in this case, I do not fully understand the implications of this race condition between the clock tick and the device programming sequence. And it seems to me that the initial statement here, which stops the clock, and the final statement, which restarts the clock, they're redundant. So I remove them. I could make any other changes to this code. And then I tell the tool, okay, so I want to start this. I want this function to start this way. Now generate the rest of it. There are two things that can possibly happen now. Number one, the tool will actually find a way to extend my not really correct implementation to a correct one, or it will tell me that there is a problem. You can try to guess what happens in this case. So let's see. That didn't go so well. Sorry. Okay, so the tool figures out that although what I did was wrong, it can still stop the clock and write the correct value. So it actually found a way to still complete the request. Okay, this is where the developer gets really annoyed. And here's where I say, okay, forget about it. I want the implementation to look like this. I removed my placeholder for synthesized code. So this is my implementation. Stick to it. And then I move on to the next function. And I ask termite to synthesize code for that. So what happens now is termite simulates everything I wrote so far. And it computes a set of all states where the game could be after executing my existing code. And it figures out that some of the possible end states are error states. There are states from which there is no winning strategy. They're outside the winning region of the game. And it's telling me this. It can also produce a counterexample which will show me exactly what's going wrong, which I'm not showing for time reasons. But it can give you an explanation of exactly what the problem is. So given this kind of user-guided tools, there are several scenarios you could follow. Number one, you could still do full automatic synthesis, right? You give it an empty template for the driver, and the tool produces a complete implementation. In practice, we found that the hybrid approach is much more practical. It's where you start with the empty template. You get termite to synthesize some of the code for you. But then you go and somehow refactor this code. Maybe you add some structure to it, especially in like more complex drivers than what I just showed. You can amend it with other operations. You can make some implementation choices. And then you go back to termite and ask it to produce more code. And you continue until you have a complete implementation. But you can also take this to extreme. You can actually write the whole driver by hand and give it to termite. And termite can still do synthesis and game solving. And it comes back to you and says, I found a way to synthesize the driver for this case, where I already wrote everything by hand. What it really means is that it verified the driver that you wrote. So without any extra effort, without having to implement anything else, termite doubles as a verification tool for drivers as well. So one more thing I wanted to discuss is how do we write specifications. I'm not going into details of how OS and device specs are produced, but one observation I wanted to share is that we found that if for each driver we start and write the OS and device specs from scratch, well, it's just easier to write the driver. It's more work than writing the specs is more work than writing the driver, which kind of defeats the purpose of synthesis. Fortunately, we can work around this problem by relying on specification reuse. So first, let's talk about the OS specs. So it turns out that the specs are largely generic, right? Because a class of devices has to implement, a class of drivers has to implement a common interface with the OS. Now, having said that, every device has additional features, which are not part of the generic spec, but these features tend to be extensions of the generic spec. So by writing one generic spec for a class of devices and for the OS, we can then reuse them with small changes for multiple drivers. Of course, we cannot do this with the device spec because by definition they are device-specific. Fortunately, we can reuse existing specs. Specifically, we can reuse specs written by hardware designers as part of the hardware development process. Specifically, we rely on a class of high-level specifications known as transaction-level models, which are created for the purposes of simulation, hardware testing, early design exploration, and so on. So these high-level models, they tend to model the device at exactly the level of abstraction we need in synthesis, which is nice. Having said that, at the moment, we don't have a front-end compiler from a hardware description language into the termite specification language. So we still write our specs by hand, but we write them by either automatically translating from, manually translating from existing transaction-level models, or by writing them based on documentation, but using the same modeling style that you would use in a TLM model. Okay, so we used our tool to synthesize a bunch of drivers for simple but realistic devices. The most exciting ones being webcam and hard disk. The other ones are typical devices found in many embedded systems like I2C, SPI, serial controllers, clocks, and so on. You might notice that in terms of the lines of code, our drivers are smaller than you would expect a Linux driver to be, for example. Which brings me to my next point, which is explaining the scope and limitations of what we're doing at the moment. So first of all, we are really focusing on synthesizing the device control logic of the driver, as opposed to all the boilerplate code of which there is so much in, for example, drivers in Linux. All this code responsible for resource allocation, binding to various OS resources, creating sysfs entries. All of that must be provided manually or synthesized using some other method, and it must be added as a wrapper around a synthesized driver. At the moment, our drivers are sequential in the sense that they assume that every driver entry point is invoked atomically. But having said that, we are working with researchers from CU Boulder and IST Austria on building another tool that takes the sequential driver and adds synchronization code to it automatically so that it can safely run in the multi-threaded kernel environment. Still work in progress, though. And finally, one important limitation we still have is that we don't support synthesis of code for handling DMA. This is an important limitation because many devices nowadays use DMA. It's work in progress, and I'm hoping that in a few months we will have a version of Termite that has DMA support as well. So there are a few takeaway points that I'd like you to take from this talk. So we developed this tool that automates the tedious parts of driver development. At the same time, the user is still in control. The user can write any manual code, but Termite enforces correctness on this code. Now, given the limitations we still have, it would be too early to say that we have solved the driver synthesis problem completely. But we did synthesize realistic device drivers, and that's to us a clear indication that driver synthesis is less impossible than previously believed. Thank you very much. I'm happy to take questions.
Hi, Ardalan Amirisani from Ryzhyk. Great work. I was just wondering, when you're interacting with termite, right, and it's generating code for you, is it going to be hard for me to figure out what the code is that's being generated doing? So, like, isn't that some additional effort? So I have to understand what it's doing, whether I want to change it or not, or do you have any experience with that?
Yep. So the kind of expertise you need to have to use Termite is basically the same expertise you need to write the driver. So you need to understand what's going on. We have tools that help you. So you can, for example, if something doesn't make sense, we have pretty much a standard interactive debugger where you can step through this code and you can simulate both what the driver is doing and what the device is doing. And you can figure out how this changes device state. You can also, if something doesn't look right, like I showed you, can change it. And Termite will it's either okay, and you can still control the device, or it will show you what you're doing wrong. So there is tool support for helping you, but in the end of the day, you have to understand what you're doing. It's not like completely magic, magic bullet which will do the things for you.
Thank you.
Gilles Muller, Emilia. So this is a great tool. I'm wondering, instead of generating real code, would it be interesting to generate a default specification which, in fact, describe what the device does and would make the device and at least what you're generating much more understandable by the programmers?
Yep. Actually, I think a better strategy would be to change our specification language, of which I didn't really talk at all, to be more Devil-like, or at least to include Devil-style syntax, so that already in your specification of the device you have Devil-style register description, register layout description. But it could also then be part of the generated code as well.
Joe Tuchek, HP Labs. Very good. Also, honestly, you say you don't do DMA. On that point, what do you think is difficult about getting DMA? And would it be possible to have the developer, do the DMA bits and have Termite take care of the rest?
Yep. So that's what we do at the moment. If you want a DMA-enabled driver, you have to write the DMA code yourself. But then you end up for many drivers, all the interesting code is in DMA. So we'd really like to automate that as well. The difficult point is it's not even the fact that you're moving data between memory and the device. It's the fact that most of the time DMA involves some kind of data structure in memory, like a circular buffer or list. And if you model this in a sort of straightforward way in our game-based framework, you end up with a state explosion. And basically what we're doing now is coming up with clever ways to avoid the state explosion.
Scott Moore from Harvard. I really enjoyed the live demo. I was wondering if you'd show us the counterexample, if we have a little time.
I'm happy to do so, probably better offline after the talk.
Hi, Brad Morey again from HP Labs. So this is totally cool. It's got the same sort of thing where you're helping people do stuff that they couldn't or was hard to do beforehand. I like that. You briefly put some numbers up about how long it takes to run the games. Is the thing that you're doing? It's obviously exploring a state space. Is it doing that? Is it parallelized? How does it scale?
Okay.
What's the memory footprint? All that stuff.
Yep. So this is a good question because, to be honest, 90% of this project is about developing a scalable game solver.
Right.
Because it turns out that in this project we're basically the first ones to use a game like two-player game theory for anything real, yeah. Which means that none of the algorithms that existed are really useful. So I think we got it, and we have separate publications about that, but I think we got it to the point where for the devices we want to synthesize, it's not the main bottleneck anymore, performance and memory. I think that once we have DMA support and we move on to more difficult stuff, then we will probably hit this bottleneck again, and so we will have to do more stuff. But for simple devices like this, it's not really a problem.
Is it parallelized?
No, not at the moment, but we're actually working with, it's based on the BDD computation at the bottom. And one of the things we're doing is we want to switch to a parallel BDD solver once it exists.
Very good. Thanks.
Thanks.